Heard of an approximation function? Well, it's really interesting, those topics, because they are underlying how we represent data points in the space, which actually can become parameters or targets that we're looking for. And to have it as a function, that means that we're trying to use mathematics to try to describe in a space, so in a visual way with numbers and how they evolve, these patterns or how our data is appearing. So for example, objective function. Normally, an objective function is something you want to minimize, you want to maximize. For example, you want to reduce a cost, you want to achieve a higher number of sales. But what's the difference with an approximation function? Well, an approximation function, it's the function which finds a best fit model, but does not actually represent exactly how the data or the parameters you're looking for to represent really are describing reality. Why? Because maybe the pattern they follow is so complex that the maximum we can get is just an approximation function. What's the difference between approximation and interpolation? Well, when you have a function, you can basically aim to pass through every data with that function point describing a curve. While when you have an approximation function, the curve of the function tries to describe the data in, for example, groups, clusters, or any other, in a more approximate way, of course. Approximation functions are widely used in machine learning, data analysis, scientific computing, and engineering, of course. But, well, I'm sure that without going into, maybe you're a mathematician lover, and well, of course, you know some of the polynomial, you know, linear, typical x equal to y a plus b, or where usually it's the opposite. It's y equal to x multiplied by a plus b. That would be a line in the space, typical 2 dimensions, you have your line. But if you go a bit further, let's imagine you want to do regression techniques. What are regression techniques? Regression means I'm going to create a function which is going to, based on the limits of application of the data universe, where I'm going to first have, for example, from 0 to infinity, from 0 to any number, from minus infinity to plus infinity. I'm describing the universe of numbers. Based on the historical data, I'm going to create a function that can enable me to predict where in one of the x's, whether it's x, for example, I'm going to find y. So basically, a classic technique like linear regression, that's the technique that models the linear relationship between the input variables and a target variable, in this case, y. But well, that's the simple way of seeing things. But then we have, just for you to mention, of course, you already know probably, polynomial regression. Well, polynomial regression extends linear regression by feeding a higher order polynomial function to capture nonlinear patterns in the data. Nonlinear patterns are, of course, much more complex. And of course, a high order polynomial function, you can imagine, it goes beyond sometimes the human representation, for sure. But well, what another type of, now that I remember, there is another type of functions that's really useful that you maybe have heard of, and those are functions in logistic regression. And this is a bit different because usually when we talk about regression, we think about forecasting, but logistic regression, we are forecasting, but we are doing binary classification. That means we are trying to predict whether a set of data belongs to one class or to another. And what is the name of that function? The sigmoid functions. Sigmoid functions look like sinus, cosinus, but do not have to do, as they just go from the minus space to the higher space, doing a kind of an S. They are not periodic as the trigonometric function, but just to have a visual interpretation. So yeah, the sigmoid function that widely used in logistic regression. So basically, the approximation functions are very used. They're very used, for example, in neural networks. There are highly versatile functions which are capable of modeling complex nonlinear relationships in the data. They can learn from examples and make accurate predictions. And with those examples, they just build those functional approximations which are constantly updating. And that's how it works. In deep learning, also deep neural networks with multiple hidden layers, they can learn integrate patterns and features in high dimensional data, making them powerful for tasks like image recognition and natural language processing or whatever. Training algorithms, of course, when you want to train an algorithm, then I'm talking about, for example, neural network. You can use backpropagation, of course, to allow the neural network to optimize their internal parameters and weights based on minimizing the errors between predicted and target output. So go back again and retrain, sometimes using online learning, but that's another. There is something that also you might have heard, and it's important to talk about. We're talking about the kernel method. What's a kernel method? Well, a kernel method, it's a non-parametric method that, well, the main thing is that we're not going to make assumption about how the underlying data of the distribution, is. That means that allowing to capture complex nonlinear relationships, we just, let me see how to explain this. A kernel function is a high dimensional function that calculates the distances between the products of all pairs of data points. So that means that it's a quite complex kind of function which is going to represent, for example, in computer vision, my image based on some points, and by multiplying the product, I'm talking about algebraic products. There are several ways of using those products. It will enable me to operate in these dimensions, these spaces where there are so many dimensions for me to operate that I would get lost. And those are not approximation functions. They are different because we're talking about algebraic functions. The idea in the kernel method is to measure the similarity between data points using points which are actually kernel functions, which can then be leveraged for classification. The kernel methods are used, for example, in support vector machines or Gaussian processes. Those can be very efficient, making very attractive for machine learning because they enable to represent all those data points based on the products. One thing, the other day I was listening to a podcast from Lex Fridman, Well, he has a really nice interview with Vladimir Vapnik, which was one of the creators of the support vector machine. And it's really interesting because from a mathematical point of view, and for clustering, for example, or for other machine learning applications, support vector machines and kernel methods are really, really interesting. We have plenty of other functions. There are many types of function, radial basis, which happens in the space, like reality of the environment. But what it's important to know is that the function approximation techniques, they are crucial in various business applications. They enable accurate prediction and decision making, from, for example, sales forecasting to customer churn analysis. These methods, they help organization optimize operations and patterns, gain insights, you know the drill. Business leverages functions approximation the model to complex relationships between price, products, personalized services, ultimately improving efficiency, ultimately improving the customer satisfaction, healthcare, drugs development, plenty of application. So those statistical perspective on the function approximation, it's what really matters, not so much the mathematical way of how they are being built. So from a statistical standpoint, the function approximation are the techniques that are essentially tools for modeling complex unknown relationships between variables. How? By feeding parametric or non-parametric models to the observed data. These methods allow us to make predictions, that's sure, but I was thinking also inferencing underlying processes that maybe we didn't have discovered. So regression analysis, we have already said, with our dependent and independent variables, of course, which one of them usually is time. Time is a classical variable, independent variable. The kernels, methods, the Gaussian approximation, very flexible for non-parametric approaches. There are others. Now I'm thinking about if we like those functions, if we like mathematics, if we like this approach, that doesn't mean that if you want to take care of doing some important, interesting studies, important jobs, important tasks for you to apply in your business or in your company, that means that having the mathematics understanding about how the data is going to be processed, is going to be melanged, it's going to be moved around, agitated. That's how abstractly it's going to represent the world. So the more you understand that basically those transformations are actually setting parameters or aggregating the data as a statistical matter, the more you're going to like how those already built, some of them for most of us which use those algorithms they can represent some real value and real usage in our daily tasks. All right, so righty. Have a good one and see you soon.